In this problem, we are given a stress element aligned with the x and y axis in figure 1. In part A of the problem, we are asked to find the state of stress sigma n, sigma t, and tau nt when the stress element in 1 is rotated by an angle theta. Let's look at the case when theta equals to 30 degree. For stress element 1, we will have sigma x equal to a tensile 30 MPa, sigma y also equals 30 MPa, and tau xy equals to a minus 15 MPa. Remember that as per convention, a counterclockwise shear stress on the positive x face is considered positive. In this case, we have it reversed, so hence the negative sign. To find out the normal stress, we have sigma n as per this expression from the textbook. So if we were to plug in theta equals to 30 degree, we would end up with sigma n equals to 30 plus a 30 divided by 2 plus a 30 minus 30 divided by 2 cosine 60 degree plus a minus 15 sine 60 degree. With the second term going off to 0, we are left with sigma n equal to 17 MPa. We are then asked the value for sigma t. If we scroll up and look at the angular difference between the n and the t axis, we see that they are 90 degree apart. So if we were to use the same formula for sigma n, but now replace sigma theta by theta plus 90 degree, we would have our answer for sigma t. So in this case, theta plus 90 degree equals to 120 degree. Therefore, 2 theta prime equals to 240 degree. Therefore, sigma t becomes 30 plus a 30 divided by 2 plus a 30 minus 30 divided by 2 cosine 240 plus a minus 15 140 degrees. The second term going off to 0 again, we are left with sigma t equals to 43 MPa. Again, if we plug in theta equals to 30 degree in our expression for tau nt, we'll end up with tau nt being equal to a minus 30 minus 30 divided by 2 sine 60 degree plus a minus 15 cosine 60 degree equal to a minus 7.5 MPa. In part B of the problem, we are asked to calculate the two in-plane principal stresses and their angular position. We have sigma average being equal to sigma x plus sigma y over 2, which in this case becomes 30 MPa. R becomes equal to sigma x minus sigma y over 2 whole square, which reduces to 0, plus a tau xy whole square. Since this is the only term remaining, R is equal to mod of tau xy equal to 15 MPa. The magnitude of the maximum principal stress, sigma 1 equal to sigma average plus R equal to a 45 MPa. And the in-plane minimum principal stress, sigma 2 equals to a sigma average minus R or 15 MPa. Find the angular position of the principal stresses. We have sine 2 theta p1 equals to a tau xy divided by R or a minus 15 divided by 15 equal to a minus 1, and cosine of 2 theta p1 equals to a half sigma x minus sigma y over R. Since sigma x is equal to sigma y, we have cosine of 2 theta p1 equal to a 0. Let's draw out a circle involving sine and cosine. If we look for sine equal to a negative 1 and cosine equal to a 0, we find that the angle theta, or theta prime in this case, equals to 270 degree. Therefore, 2 theta p1 equals to an inverse sine of minus 1 or 270 degree. We can also say that this is equal to a minus 90 degree. Theta p1 equals to 135 degree or 45 degree, negative 45. Since both angles are 180 degrees apart, it's essentially the same thing. To find out the position of the minimum principal stress theta p2, we know that theta p1 and theta p2 are 90 degree apart. So we can say that theta p2 equals to minus 45 plus 90, that is equal to a 45 degree, or 135 plus 90, that is equal to a 225 degree. Again, both 225 degree and 45 degree are 180 degrees apart, which makes no difference.